This is the chapter 7 about hydrodynamic techniques. I'd like to focus on this word, dynamic. In this case, the meaning of dynamic is to induce the convection or the movement of electrolyte around the surface of electrode. Up to now, we didn't touch the electrode without any movement, or we didn't stir or agitate our electrolyte. So I could say the techniques you have learned up to now is the hydrostationary techniques. However, from this chapter, we could use the convection of electrolyte for using the benefit of hydrodynamic techniques. For the hydrostatic techniques you have learned up to now, we have used the simple diffusion equations because we didn't have any convection, we didn't have any migration. So only thing we should consider is the diffusion term. The driving force of which is the concentration gradient. So most of the equation in the mass transfer limited system came from the diffusion equations. However, in these hydrodynamic techniques, we should derive more complicated equations based on the diffusion plus convection. You could meet very often this kind of words, RDE and RRDE or double RDE. RDE stands for rotating disc electrode and RRDE stands for rotating ring disc electrodes. It means we will rotate our electrode instead of the stationary mode of electrode. You could find the content about the hydrodynamic techniques in the chapter 9 in the Bard and Faulkner book. Here is the basic equation about the mass transfer. The mole flux J of a specified species J have three different terms here. The first term is the diffusion process, the driving force of which is concentration gradient. And I have said up to now you have used this term for solving some problems. The second term is the migration process, the driving force of which is the potential gradient. This migration process is very useful for the electrophoresis. Usually, we need to apply a very big potential into the system. In the hydrostationary electrochemical techniques like cyclic Bolt homogram or something like that, we have tried to kill the second term or migration process by adding some supporting electrolyte in our systems. Let's go to the last term, which is the convection. Finally, we have the convection term here. The velocity is the driving force of the convection term. In the hydrodynamic technique, we'll use the third term plus the first term to solve the equations or governing equations of the mass flux or mole flux in the hydrodynamic techniques. Let me think about the benefits of hydrodynamic techniques. Hydrodynamic techniques is based on the convection. More accurately, I could say that is the rotational mode of the electrode. Then, that electrode motion would induce the faster mass transfer of electroactive species or supporting electrolyte inside of electrolyte. So here's some merit of using hydrodynamic techniques. The first one is a steady state is quickly obtained because we are rotating the electrode and based on faster mass transfer. The second thing is, or second benefit is, we would obtain a thinner diffusion layer. So we could suppress double layer charging. Double layer charging is not involved or less involved in the whole process. So we could focus on the Faraday reaction rather than the non-Faraday reactions. The third benefit is small contribution of mass transfer to whole process. So charge transfer is emphasized in the hydrodynamic techniques. Here is some question. Is time variable lost in the hydrodynamic techniques? Because I have said a steady state is quickly attained. What is the steady state? The steady state is the time invariant systems. So this question is very good question. Is time variable lost because we have obtained the steady state? My answer is no. Even if we don't have the real time variable, but instead of it, we could control the rotational rate or solution velocity. So at the higher rotational rate or higher solution velocity, we could experience the change the electrochemical signals when compared with the situation at the slower rotational rate or solution velocity. So we have the time variable like rotation rate or solution velocity. There is a big difficulty. How can we set a reproducible, I'd like to emphasize this word, reproducible mass transfer conditions? Try to agitate or stir the electrolyte with your stirring bar, magnetic stirring bar. Sometimes you could observe some turbulence, which is the unexpected the velocity profile developed. So we should control the convection in the very detailed and very minute control. So how can we set such a reproducible mass transfer conditions? We should use a more specialized machine for this experiment. This is the rotating ring disc electrode system, including rotating just disc electrode system. This is the commercially available product for this hydrodynamic technique experiment. Here is the electrochemical set, beaker, the yellow electrolyte, and we have the working electrode here. On the tip of this electrode, you could find sometimes glass carbon, gold, or platinum. This electrode is this one. So here's the electrode body, which is the Teflon, and on the center of the disc, you can find some conductor, glass carbon, gold, platinum, and this electrode have a shaft. The shaft, the tip of the shaft, you could find the conducting electrode here. So this one, the shaft is connected to the electric motor, and then you could rotate the electrode, working electrode. Also you can find reference electrode and the counter electrode. Everything is the same of the hydrodynamic technique. Between hydrodynamic technique and conventional hydrostationary techniques. Only different thing is that we will rotate this electrode. This schematic describes the whole system of this rotating disc electrode system, and also this is the schematic only about the rotating disc electrode. Here's the shaft. On the tip of the shaft you can find the disc electrode, and then around this shaft we have the electrode body, which is the Teflon usually. From the bottom view you can find the disc of platinum or glass carbon or gold. And then by using the electric motor we will rotate this shaft, and resultantly we will rotate this disc electrode in this way. Then what happens inside of electrolyte? We will develop some velocity profiles. Okay, this is the electrode and this is the electrode surface. Right now this electrode is rotating in this direction. What happens? Let me think about a single molecule sitting on the surface of electrode or rotating disc electrode. This molecule is thrown away from the center to the outside of electrode when you rotated the shaft of electrode. Then what happens? We experience the lag of molecules on the surface of electrode. Then some molecules is moving toward the surface of electrode, and then that is thrown away from the center to the outside. So finally we could find the this kind of streamline here, from the bulk to the surface and to the outside, from the bulk to the surface to the outside of electrode, like that. Then we could measure some signals based on this kind of velocity profile or streamlines. It's time to derive the governing equation for the hydrodynamic techniques, which is called convection diffusion equation. Let me start with the mole flux equation. I have shown you in the previous slide. Mole flux J of a specified species J is equal to the diffusion term and migration term and convection term. In this case, we'll kill the second term, which is the migration term, and also we will survive the velocity term or convection term. So we have two terms on the right hand side of this equation. So mole flux is described by diffusion plus convection. The mole flux is the vector, and also the gradient of concentration is vector, and also velocity is vector. So in the mole flux equation we have a vector term for the all terms on the left side and right side. Velocity is the vector, so we have three components of velocity in the Cartesian coordinates. For example, the velocity vector in terms of x and y and z is divided into three terms. For x, I mean x component velocity and y component velocity, z component velocity, with the unit vector for x-axis, y-axis, and z-axis. We have gradient here, gradient of concentration, even if we will kill the second term, but anyway, the gradient of potential. What is the gradient operation? the gradient of a function is df dx with some unit vector in the x direction, df dy in the with the unit vector in the y direction, and df dz with the unit vector in the z direction. I mean, the gradient operation is the first derivative operation having a vector direction. So that is the gradient operation used in the mole flux equation. Let me taking the both sides with the divergence. By the divergence operation, finally we have converted the mole flux equation into the final governing equation, which is called convection diffusion equation. Let me check what is the divergence operation. Divergence of the vector function f is equal to the inner product between the gradient operation and the function f, the vector function f. It means the final description of this operation is the first derivative of f in terms of x, in terms of y, and in terms of z. The gradient operator is the vector, and also the function, this function is the vector. So the resultant product of the divergence operation is going to the scalar. So let me take the divergence operation of mole flux equations. Then it is going to there. So let me check the left hand side of the mole flux equation. The unit of this mole flux is mole per unit area per the time. And the unit of divergence operation is 1 over some dimension, length dimension, because divergence operation is also the first derivative operation, even if this operation includes the inner product. Anyway, the unit of divergence is 1 over centimeter. So after taking the mole flux equation by the divergence operation, then the unit is going to mole, the same thing, and the square centimeter is going to the cubic centimeter after taking the 1 over centimeter per second. So mole per centimeter, cubic centimeter is concentration. So let me say, after doing the divergence operation for the mole flux is going to the d concentration dt, the unit of which is mole per cubic centimeter per second. So J is going to dc dt after the divergence operation. And also in the mole flux equation, we have the gradient of concentration. This term is going to the Laplace operation of concentration. What is the Laplace operation? Laplace operation is the divergence of the gradient of the function. So it means the Laplace operation is the second derivative operation in the form of scalar. So after divergence of the gradient concentration is going to Laplacian of concentration. And velocity here, concentration is the scalar. So after doing the divergence operation of this term is going to velocity inner product the gradient of concentration. The concentration is going to the gradient one with inner product. So this is the final equation of the governing equation for the hydrodynamic technique. Okay, so this equation comes from the previous slide, and then let me specify and simplify this very general version of the governing equation, which is called convection diffusion equation. I have said we could obtain a benefit by using the hydrodynamic technique. The steady state is quickly obtained. So, we could assume that the hydrodynamic technique experiment is proceeding under the steady state condition. Steady state means time invariant, so dc dt is going to 0 because the concentration is time invariant. Then we obtain the inner product of velocity with the gradient of concentration is equal to the diffusibility with Laplacian of concentration. As you expected, the cylindrical coordinate system is appropriate for this RDE problem. This is the electrode, the top of the electrode, and then the y-axis could be set into this direction, and r direction here, I mean radial direction, and also on the surface of electrode we are thinking about the angle of fluid, phi. So this term is going to here in the cylindrical coordinate system, and the Laplacian of concentration going to there. So let me check it. This left hand side of this governing equation is going to the r component of velocity with dc d radius plus the phi component of velocity per r with dc d phi, I mean the angle on the surface of electrode, and the y component velocity with dc dy is equal to diffusibility with the second derivative of the concentration in the cylindrical coordinate system. Actually, we don't need to think about all terms in these convection diffusion equations because the concentration is only the function of y, not the function of radius and not the function of phi. Concentration gradient is available only along y-axis. So we could keep the r term, I mean d function d r term, d function d phi term. Also the second derivative have the same elimination. This one, r term, and phi, the angle term. So the whole equation is very simplified into this equation. Y component of velocity with dc dy is equal to diffusibility with the second derivative of concentration in terms of y. Okay, then we'll solve these equations. Right now, what we need is the information about the y component of v. The y component v is the function of y or phi or r. Anyway, this ODE, or I mean the ordinary differential equation, has only y. So we will think about the function of the velocity in the y component as the function of y. I mean vy would be the function of y. So velocity information is required. We cannot get the velocity profile in terms of y from this governing equation. After getting the function form of the velocity and then introduce that function into this equation, then we could solve this problem. Then finally we could obtain the concentration profile in terms of y. Okay, then let's try to obtain the velocity profile. By rotating a disc electrode, a flow of electrolyte along the streamline is developed. I have said about the velocity profile here in this picture in the previous slide. So again, let me say again, I am rotating this electrode in this way, in this direction. So some flows is developed on the surface. Also, some molecules is thrown away from the center to the outside of the disc electrode by the centrifugal forces. So for providing the new mass of molecules into the surface, the flows from the the flow is developed from the location far from the surface into the location on the surface. So flows is going from here to the surface and then going away from the center to the outside of the disc electrode. So velocity would be the function of y in this direction and radius in this direction and phi on the surface of electrode. We could obtain the velocity profile by using two equations. The first one is continuity equation, which indicates divergence of velocity is 0. That is the continuity equation. The other thing is Navier-Stokes equation. You would learn about that from some transport phenomena or something like that. So let me try to understand the Navier-Stokes equation. Here, density with dividity. What is that? It is identical to the Newton's second law of motion. F is equal to ma. dv/dt is acceleration, and here's the density. It means mass per volume. So the left side of this Navier-Stokes equation is the Newton's second law of motion. This force is divided into three terms. The first term is about pressure development. The second term is frictional forces based on the viscosity of the fluid. And the last term is the additional force, and we could ignore the third term on the right hand side of this equation. By using this equation, then we could obtain the velocity profile. Let me get one more step. So this equation going to there after dividing both sides of that equation by density. So dv/dt is equal to -1 over density of fluid with pressure development plus some the viscosity per density was defined as the new parameter, kinematic viscosity, with the same term plus the additional force per density. That's it. Actually, those two equations are identical, but in this second equation, I'd like to emphasize this term, this parameter, kinematic viscosity, which is defined as the viscosity per density. The unit of kinematic viscosity is identical to the unit of diffusibility, like centimeter square per second. I mean, the fluid is characterized by kinematic viscosity by this single parameter in this equation. So we would recognize that the value of kinematic viscosity is very important thing. In this table, you could find some kinematic viscosities. Water is about 0.01 and acetone is 0.004 or something like that. Okay, anyway, let's get back to the governing equation. And by solving this equation, these partial differential equations, we could obtain the velocity profile. Of course, we need to have the boundary condition to solve these partial differential equations. So at the disk surface, at y equal to 0, the radial velocity is 0 on the surface, and the y directional velocity is 0 because this is the blocked end. The electrode surface is blocking the flow, so the y component of velocity is 0 on the surface, and velocity of phi component or phi component is equal to omega r, making the centrifugal forces. In the bulk solution, at y is approaching infinity, of course no radial velocity, no angular velocity, but the velocity of y at the location far from the surface of electrode is some constant velocity. Minus means the flow is approaching to the surface of electrode. So we have this kind of boundary equations. 1 PD and with the enough boundary conditions, we could solve the problem. Finally, the solution is the velocity profile as the function of y in this direction and r radius and phi. Okay, then let me assume that we have solved the Navier-Stokes equation with the continuity equations. Then here is the solution. This is the y directional component of velocity. V sub y is the function of y. Only the function of y. So Vy is equal to the product of two terms. The first term is omega, kinematic viscosity, root square. Omega means the rotational speed. And the second function is described by gamma, and gamma is a kind of y with angular frequency. So again, Vy, the y directional component of velocity is the function of y with a fixed rotational speed and also a fixed kinematic viscosity. So let me draw the y directional velocity profile here. Here is the rotating electrode at y equal to 0, and here y is going to infinity. Then at the location far from the surface, the velocity is maximized, and when the flow is approaching the surface of electrode, the velocity is decreasing like that. And then finally at y is equal to 0, you don't have any flow velocity on the surface of electrode in the y direction. Around the surface, the velocity profile can be simplified into this equation. Vy is equal to just y square. So around the surface of electrode, the velocity can be described by some parameter with y square. That is the y directional velocity profile. How about the radial velocity, which is the function of y and also radius? V sub r is equal to r radius with omega, the rotational speed, with the function of gamma. And I have said gamma is a kind of y if the rotational speed and also kinematic viscosity are fixed. So let me draw the radial velocity profile and y direction and radius. So at the location far from the surface of electrode, of course the radial velocity is 0. You have read the same thing in the boundary condition in the previous the slide. And then when the flow approaches the surface of electrode, the radial velocity is increased, and at a very critical position the radial velocity was maximized, and then the velocity decreased along y direction. At the surface of electrode, the radial velocity is 0. Okay, and also let me I have said the radial velocity is the function of r. So I have two curves here. This curve indicated by 1 is obtained at some smaller radius. This is the second curve, which is obtained at the longer radius. I mean more outside of the disc electrode. Then around the center, the velocity profiles are not very strong. However, when we are going to the outside of the disc electrode, the velocity development is more clear and evident like that. Anyway, the maximized radial velocity could be obtained at the location optimized far from the electrode surface. Also, more outside of the disc electrode, you could find higher velocity when compared with the center. So that is the situation about the velocity profile. Anyway, what we need is the y-directional velocity component of the velocity for solving the ODE for the governing equation for convection diffusion equation. Okay, so right now we have had the convection diffusion equation on our left hand side, and on our right hand we have the velocity profile, which is obtained from the Navier-Stokes equation with continuity equation. So this is the governing equation, which was simplified in our situation. So again, V, the velocity in the y component with the first derivative of concentration or gradient of concentration is equal to diffusibility with the Laplacian of concentration. Then also we have already known that the y component of velocity, which could be described by the gamma function in a complicated case. However, around the electrode surface, this v sub y is equal to, with some parameter, by the y square. That's it. So right now we have a complete form of governing equation. And here is the boundary condition. I'd like to think about the extremely mass transfer limited system. It means the overall kinetics is determined by mass transfer. It means charge transfer kinetics is much larger than the kinetics of mass transfer. So charge transfer was fast enough to reduce all oxidized species completely. So it means at y equal to 0, the concentration of oxidized species is going to 0 because our charge transfer kinetics is really fast. So this first boundary condition is based on my assumption of mass transfer limited system. And in this hydrodynamic technique, this mass transfer limited system or condition is called limiting current condition. Again, limiting current condition. The other boundary condition is like that. Far from the surface of electrolyte. I mean, in the bulk electrolyte, the concentration of the oxidized species is the value I have introduced at the initial time of the experiment. So CO star, bulk concentration. Then, right now, we have a governing equation, which are the function of y, and also two boundary conditions, because this is the second order ODE equation. So we could solve this equation. Then, here is the result. The result include CO star, that is the constant value, is equal to the first derivative of concentration at the surface with some parameter term. By the fixed first law, current is defined by NFA diffusivity with the surface gradient of concentration of the oxidized species. Then by using this equation, we could describe the limiting current. I have said we are thinking about mass transfer limited system, and at this condition, the current is the limiting current. Finally, we obtain the expression about the limiting current. Current at limiting condition for the cathodic current, sometimes anodic current. So limiting current is described by some parameters. This equation is very well known and also famous equation, which is called Levitication. Levitication is describing the limiting current, not just current. Limiting current is obtained by Levitication. Let me check the terms in the Levitication. Again, limiting L, current I, for the cathodic process C is equal to 0.62. So number of electron transfer, Faraday constant, and area, the electrode area, NFA, is all together in many equations with diffusivity of oxidized species to the 2/3 and angular frequency term, not angular frequency, the rotational speed, the root square of rotational speed here, and kinematic viscosity to the -1/6 with just bulk concentration. The most important point is the rotational speed. Levitication is saying that the limiting current is proportional to the root square of the rotational speed. It's very important thing. So we could define the Levitch constant. Levitch constant is limiting current per the root square of rotational speed omega per bulk concentration. This value, I mean the value of Levitch constant, is always constant at a fixed electrolyte and electrode, independent of the rotation speed. So that is the Levitch constant. Anyway, the most important thing is the limiting current is proportional to the root square of omega, rotational speed. We could easily extend this Levitch equation into the non-limiting current expression. The non-limiting current here, then everything is the same, this part and this part, with CO star minus the surface concentration of the oxidized species. This second concentration term is going to 0, then we could obtain the Levitch equation at the limiting current condition. Okay, so right now we have obtained the Levitch equation, and here's the Levitch equation which is presented in the previous slide. And let me check the concentration profile in the hydrodynamic technique. We are focusing on the y-directional concentration gradient. I have said about that. And far from the surface of electrode, here is the electrode surface, far from the surface of electrode, we would have the constant concentration, which is the bulk concentration. However, after the specific location, I mean within the specific the distance from the electrode, the concentration is going down, and then finally which is going to 0 on the surface of electrode, which is the limiting current condition. Levitch equation can describe the limiting current term even in the equations derived from non-rotating situations. Here is the first example, which is the diffusion layer model. You have learned about the diffusion layer model in the previous chapters. In the simple steady-state diffusion layer model, the limiting current for the cathodic process, or sometimes anodic process, can be described by the product of an FA and the ratio of diffusibility to the diffusion layer length and the bulk concentration. Of course, the limiting current can be described by Levitch equation, where the current is proportional to the root square of the rotational speed. By combining this diffusion layer model equation with Levitch equation, we could obtain the rotational speed dependency of diffusion layer thickness, delta. That is to say, delta of oxidized species is inversely proportional to the root square of omega, or the root square of rotational speed. It means as you speed up rotating the disk electrode, the diffusion layer thickness decreases, or faster rotation results in the thinner diffusion layer. This is a kind of the of course thing. Faster rotation is going to the thinner diffusion layer. It was the benefit of the hydrodynamic technique. Let me go to the second example. Reversible mass transfer limited system. This is the current voltage curves for the mass transfer limited systems. At equilibrium, the current is 0, and when we are going to the more negative potential, or sometimes going to the more positive potential, we would meet the limiting current for the cathodic process and also the limiting current for the anodic process. In this case, we could use the Levitication. I mean, this limiting current for the cathodic process, like in this equation, or this limiting current for the anodic process in this equation, is the function of the rotational speed, omega. I mean, the Levitication is working for this limiting current for cathodic and anodic processes. I mean, again, the limiting current is proportional to the root square of the rotational speed omega. Let's go to the other equation for the hydrodynamic techniques. That is the Kohlteki Levitch equations. Let me think about totally irreversible one-step, one-electron reaction. Then, disk current I can be described by NFA, in this case, n is equal to 1, with fold rate constant, which is the function of electric potential with the surface concentration of reactant. In this case, the oxidized species is reactant. The fold rate constant could be described by the standard rate constant with exponential function of minus alpha f with the potential gap from the formal potential. You can find this expression from the Butler-Balmer equations. Anyway, the current can be described by this mass action law. On the other hand, the same current can be described by the limiting current with some concentration term. Here, the ratio of current to the limiting current is the ratio of the concentration gap between bulk and the surface relative to the bulk concentration. This equation is obtained by comparing between the non-limiting current condition and limiting current condition. Right now, we have two equations, and I'd like to eliminate the surface concentration of the reactant. Then, we would obtain the current expression like that. Current is NFA with fold reaction rate constant, bulk concentration with 1 minus the ratio of current per the limiting current. Here, I'd like to define the group of the parameter as the Kohlteki current or kinetic current. That is to say, Kohlteki current or kinetic current is equal to NFA, fold rate constant, with bulk concentration. At the very first time for deriving this equation, I have said the current is defined as NFA, fold rate constant, with surface concentration. Let me compare between those two equations. In the Kuteki current, the surface concentration is changed into bulk concentration. It means there is no limitation of mass transfer, so you could find the bulk concentration even on the surface of electrode. So, the Kohlteki current or kinetic current is the current in the absence of any mass transfer problems, which is independent of rotation rate. You cannot find any parameter like rotational speed here. So right now we have some equations. And by reshuffling this equation, finally we could obtain the Kohlteki-Levitch equation. 1 over the overall current is equal to 1 over Kohlteki current plus 1 over limiting current, or sometimes which could be called as Levitch current. Again, 1 over overall current is equal to 1 over Kohlteki plus 1 over Levitch. The Kohlteki term is omega independent, where omega is the rotational speed. However, the Levitch term is, of course, depending on the omega rotational speed. So the Kohlteki term is omega dependent. Here's the graph where y-axis is the overall current and x-axis is the root square of omega, or rotational speed. This is the Levitch line because the current is just proportional to the root square of omega. I have said about that in the previous slide. However, the other line is called Kohlteki line because this line is independent of omega, and actually the value of the current is Kohlteki current, which is defined as NFA for the rate constant with the bulk concentration of reactant. The experimental data is starting from the Levitch equation, then some deviation, then finally approaching the Kohlteki current. Let me explain about that in a more detailed way. At the very slow rotation, of course, mass transfer is much slower than the charge transfer. So, at this rotational speed, the system is mass transfer emitted. Of course, the current is a kind of limiting current. So, at the slower rotation, the experimental data follow the Levitch line. However, as the omega increases, there is some deviation from the Levitch line. And at the very fast rotational speed, then it is going to the Kohlteki line. I mean, you could find the Kohlteki current at the very high rotational speed. The deviation from Levitch equation indicates the charge transfer kinetic limitation. Still, I have the Kohlteki-Levitch equation here. Again, the overall term is equal to the Kohlteki term plus Levitch term. And I have drawn some plot which is called Kohlteki-Levitch plot. Y-axis is 1 over I mean this one, Y, large Y, and x-axis is the 1 over root square of omega. According to the Kohlteki-Levitch equation, we would have the linear equation. Let me write down something here. So this is the Y, and 1 over root square of omega is x. So we could find y is equal to y-intercept, which is the 1 over Kohlteki current, plus a is the slope with x. So we should have the linear plot in the Kohlteki-Levitch plot. Then, in this case, I have two linear lines. The first line was obtained at very large overpotential. Large overpotential indicates very fast charge transfer. It means mass transfer limited system. So, the Kuteki current is very large because of the fast charge transfer. So, the y-intercept is 1 over ik, which is going to 0 because k value is very large. So, at the very large overpotential, the Kohlteki-Levitch plot is passing through the origin. I mean, the y-intercept is 0. From the slope, we could calculate the value of 1 over 0.62 NFA diffusibility to the 2/3 with the kinematic viscosity to the minus 1 over 6 with the bulk concentration. So, if you know the information about N, F, A, CO star, and kinematic viscosity, you could calculate the diffusibility. Let me decrease the overpotential. Then, this linear line moves upward to this line. The smaller overpotential indicates slower charge transfer kinetics, and it means charge transfer limited system. The slope is the same according to the Kohlteki-Levitch equation. However, the y-intercept is changing from the origin to some values because at small eta, the charge transfer, the Kohlteki current or kinetic current has some value. So, where the kinetic current or Kohlteki current became smaller. So, this value became larger when compared with the first case. So, the y-intercept could be found on the y-axis as the 1 over Kohlteki current. From this y-intercept, you could calculate the kinetic current. Again, what is the meaning of kinetic current? The kinetic current or Kohlteki current is the current without any effect of mass transfer problems. So, by using Kohlteki-Levitch equations, you could calculate the diffusibility and you could calculate the kinetic current at various potential. Here is an example for using Kohlteki-Levitch equations or Kohlteki-Levitch plot. The electrochemistry I'd like to introduce is hydrogen peroxide evolution reactions. Hydrogen peroxide production reactions. The oxygen plus proton plus 2 electron is going to hydrogen peroxide anion. This is the reduction process. So I have moved the potential from the more positive potential into the more negative potential. Then I have measured the current. At the 0.9 volt here, at the low overpotential, we cannot find any current because there are no reduction process here. However, when I scan the potential to the more negative value, the current responsible for the hydrogen peroxide production is going up, and then at the very high, very negative potential or very high overpotential, the current is reaching the saturated value, which is called limiting current. Let me say this linear sweep thermogram is obtained at 2500 RPM. Also in other RPM like 1600 and 900, 400, 100 RPM, I have obtained the similar linear sweep thermograms. By using those several linear sweep thermograms at various scan rates, then I could build up the Kuteki Levitch plot. Again, x-axis is the 1 over the root square of scan rate, and y-axis is the 1 over overall current. Then here I have plot 3 curves at 3 different applied potential: 0.60, 0.70, and 0.75 volt. 0.6 here, 0.7 here, and 0.75 here. The 0.6 volt is considered as the highest of a potential. So, at the larger of a potential, the y-intercept is going to 0 or very small values, because right now the charge transfer kinetics is very high, so 1 over Kohlteki current is going to 0. Then let's move from 0.60 to 0.7 to 0.75 volt. Let me say this 0.75 volt is the lowest of potential. From the data at various various rotating speed, I could set up the other Kohlteki Levitch plot here. And in this case, the Kohlteki Levitch plot at 0.75 volt have the same slope as the 0.60 volt case. However, y-intercept increased significantly because I am sitting on the very low of potential. So the kinetic current or Kohlteki current would have the very small value. So 1 over Kohlteki current is going to the higher value here. Then the Kohlteki Levitch plot for the 0.75 volt is shifted upward from the 0.60 volt case. All of the 3 lines have the same slope. However, you can find different y-intercept. From the y-intercept, you could calculate the Kohlteki current or kinetic current, which is the current without any effect of the mass transfer. So, by using this Kohlteki Levitch plot, you can calculate the diffusibility from the slope and the kinetic current or Kohlteki current. Okay, up to now I have thinking of irreversible reactions. In this slide, I'd like to extend the Kohlteki Levitch plot from the reversible case to the quasi-reversible case. From irreversible case to the quasi-reversible case. We have obtained the Kohlteki Levitch equation for the totally irreversible case. Then let's go to the quasi-reversible here. For the totally irreversible case, we have considered the forward reaction. However, in the case of quasi-reversible reactions, we should be thinking about the backward reaction as well as the forward reaction. So here is the Butler-Balmer equation version 2. The ratio of current to the exchange current is forward reaction minus backward reaction. Each reaction term have the surface concentration of oxidized species and the reduced species. And also we have two more equations. Current can be described by limiting current with the concentration term from the viewpoint of oxidized species and from the viewpoint of reduced species. Then, by combining those three equations, we could obtain another version of Kohlteki Levitication. Actually, this equation is the another version of Kohlteki Levitication by reshuffling this equation. Then 1 over the overall current is equal to some omega independent term like Kuteki current and omega dependent term like Levitication term. But the form is really complicated and it is very difficult to apply this equation to analyzing the experimental data. Anyway, the Kohlteki-Levitication equation could be extended to quasi-reversible case from the totally irreversible case. However, usually when we are saying Kohlteki-Levitication, this form is the most appropriate version of that equation. Again, 1 over current is equal to 1 over Kohlteki current plus 1 over Levitication current while limiting current. That's it for the rotating disk electrode system.